with this, we will start and we'll see how it goes.
Awesome. I think I'm mic'd up. Good afternoon. Nice to see a lot of familiar faces. For those of you that don't know me, I'm a final year PhD student in Alexei's group, and I've been in Singapore for the past couple of years where this work has been carried out. And before I begin, I'd just like to quickly acknowledge my team. So Jace was my main collaborator on the project. I supervised Salfraz and Robert, two undergrad students who assisted with various parts of the project. And of course, Professor Alexei Lapkin and Professor Kedar Hippelgoenka are my two supervisors. We've recently released a preprint about this work, so if you're interested in this presentation, would love to have any questions at the end of the talk, as well as there's this preprint out there. So to begin with, I'm going to give a brief overview of the liquid formulations workflow that I've been developing in Singapore, and that helps place this PH project in the broader context. I'll then go over the hardware aspect of the bot and talk about lab automation. This ties in with the theme of this lecture series. I'll then move over to the software side, looking more at the machine learning and chemistry, before wrapping up looking at a scale-up application, as well as showing you a web application. So if you want to take home the software or the titration algorithm side, you should be able to do that already. So on screen, you see my semi-automated machine learning-driven formulations workflow. This starts with a design of experiments methodology, which suggests which experiments to do. This is executed on an OpenTrons OT2 liquid handling robot, which has been retrofitted with a mass balance for accurate automated viscous liquid handling. We then carry forward those samples onto the multi-position stereoplate, mix them, and then assess them for their phase stability. We carry forward the stable samples for titration, which is the focus of this talk, before then waiting an amount of time pre-agreed with our industrial partner, 48 hours, before reassessing the formulations for their phase stability, and then once again carrying forward the stable samples for final characterization, being turbidity measurements and rheology. We also have an image data set, so we've done some computer vision work for predicting phase stability too. Now moving to the industrially motivated problem statement for this talk and this pH project. We need to adjust the pH of viscous liquid formulations with weak polyprotic titrants. So now, within this statement lie two sub-problems. One, working with highly viscous materials, and two, working with weak polyprotic titrants. So our group had previously developed a previous iteration of this pH bot to work with aqueous buffer solutions. We have Nick and Alexander in the audience that did this work, which is over here in the Department of Chemistry in the iDMT lab now. However, this nor any other commercially or academically available platform could not deal with the kind of high viscosity samples that I'm working with. Namely, it's not able to mix them up sufficiently. Further to this, if you wish to have a fully automated titration robot, then you also need to have a fully automated cleaning solution. Cleaning is an often overlooked part when you think about setting up a digital and automated lab. So these are two engineering problems which we're going to show how we solve them. And then moving over to the chemistry side, we have some previous work in our group by Alexander working on a machine learning driven titration algorithm for closed loop pH adjustment. However, this work worked with strong acid, strong base pairs such as HCl and NaOH. However, for my project, we were required to use citric acid by the industrial partner, as this is what is used in real-world formulations. Citric acid, as a weak polyprotic titrant, is able to confer the final formulation excellent buffering properties, and what this means in reality is that it means the product stays stable at the target pH for longer. So this is, of course, a great property for the product. However, it makes it a difficult titrant to use. The main problem being with HCl and NaOH, we can predict that these are going to fully dissociate as they're strong acids, strong bases. However, with citric acid, its acidic strength is in fact pH dependent. And for this project, we work with citric acid and sodium hydroxide, though the method, as I will discuss towards the end of the presentation, is more generalizable. The issue with, if you can imagine, you overshoot the set point, and then you need to kind of correct and go backwards on yourself. If you add weak acid and strong base, this is the recipe we give to a high school student for preparing a buffer system. And a buffer system, by definition, is going to be resistant to pH change. So we have both engineering and chemistry problems which need to be solved here. So this image shows you a CAD rendering of our pH bot, and I'm going to walk you through the labeled parts. So number one, we have the cosmetic jars in which we have the formulations. We're working with and titrating approximately 10 milliliters of sample volume. And you can see 6 jars in the image on screen, along with 6 more spaces, so we can titrate in a fully autonomous fashion up to 12 samples at once. Number 2, we have the washing station, which I will detail on the next slide. And then the inset shows highlighted number 3, 3D printed propeller to mix up the viscous samples. 4, a pH probe. 5, dosing needles to dose the acid and base, which are connected up to 6, the syringe pumps. So I'm now going to show you a short 1-minute clip of the pH bot in action. So it's all built on top of an Ender platform, which I'll discuss at the end of the clip. We use a lot of 3D printing techniques in our lab. And you can see the head highlighted with the pH probe, stirrer, and dosing needles. We're using tricontinent C-series syringe pumps, which are highly accurate to the milliliter. Oh, sorry, microliter. And you can see we've taken inspiration from the open transfer touch dip function to get rid of any trailing droplets on the side. And this clip gives you an idea of the viscous nature of the materials we're working with. So at the very beginning of the clip, you saw that this has been built onto the Ender platform. So Ender is a Maker 3D printer. The reason we do this is on a 3D printer, you already have the stage, which has XYZ translational motion. So in essence, you're getting this motion for free. And this also helps keep the cost of building such a pH bot down, which is great. The whole thing is being controlled by Python, and we work with like an object-oriented programming paradigm where each hardware object you see, so the syringe pumps, the pumps in and out of the wash station, the stirrer, the pH probe, everything is being defined as an object with its own methods, and these methods are then called upon in a Jupyter notebook, which is easy to use and very familiar for many people to actually run the whole platform at once. So now moving on to this chemomechanical wash station. Actually, this was one of the hardest challenges to solve, and the last thing we managed to crack to have the whole thing working. So firstly, the first solvent you might try is simply washing in usually water. However, you can imagine with these formulations, particularly we're making shampoo-like formulations, they just foam up. So that doesn't work very well. So we went to a more apolar solvent like isopropyl alcohol, IPA. And what you see here is the wash station. So we have an inlet pump pumping the IPA in. We have an outlet pump to be able to drain the tank. And with the inlet and outlet, we're able to control the level in the tank. So we fill up a solvent bath. We immerse the stirrer and pH probe in this and let it soak for a little while. And this means it absorbs up the IPA and particularly the polymeric ingredients. They begin to swell, which means they're easier to dislodge. And then we designed IPA jets. So you see highlighted number 2, this kind of toroidal ring, which has lots of holes to kind of direct jets toward the pH probe and the stirrer. The stirrer we're able to rotate during cleaning, which itself makes it slightly self-cleansing. However, the pH probe really had to be hit carefully with these IPA jets to be able to clean the rather viscous and tough residues. So we tried formulations that I prepared in my PhD project. We also tried some commercial materials, and it's had a good performance on them all. So one of the things we've tried to do within the group is we want to share the work, and we want it to be reproducible, and we want others to benefit from the methods. So my colleague Jace kindly put together this IKEA-style guide, and also you have all the materials you will need to build this pH bot, as well as more information also in the supplementary information, and everything is on GitHub in terms of the code and things to run it. And both myself and him were available to help with whichever part is needed, software, hardware, things like that. So now I'm going to move on to the machine learning and chemistry and the other side of the project. So here's an overview of the titration algorithm. So what we have, I hope it's readable from the back. What we have is we measure the initial pH. If it's not right, then we add a small random amount of acid or base in the required direction. So if it's too basic, we add some acid, and then we measure the pH. We mix the sample sufficiently. and then we measure the pH again. So we have these two initial points, which we bear in mind. And then we just go through the while loop until we iterate and until we converge on the desired pH target and pH range. So we have this physics-informed ML algorithm, which is highlighted on the top right in blue. And I'll explain what's physics-informed about it and the details behind this titration algorithm. The other thing I want to point out here is we have some constraints to this problem. So for example, if it suggests to add a nonsensical amount of acid or base, we don't want to do this, particularly because you don't want to, say, overfill the jar or create a hazard in the lab. So we will just check that the suggested amounts are sensible within the constraints, and we will proceed accordingly. So the initial stage of this titration algorithm involves taking those two data points I mentioned, 0.0 initial pH and 0.1 from the small random addition of acid or base. And then we can fit a linear regressor, a very simple linear regressor, which can be extrapolated out to the dashed red line, which is the target pH. So for all the samples in my PhD project, we've been running a very large experimental data generation campaign. We've been titrating these formulations to 5.8 plus or minus 0.2 pH units, which was a target range given to us by our industry partner. So one thing you could naively think of doing is just to extrapolate out at the red, where the green line hits the red line, how much acid do I need to add? But the problem with this, and what we know from our domain knowledge, is the titration curve has a sigmoidal shape like this. So if you are at either extreme ends, so say a very high or very low pH, not on the steep section, and you just draw a straight line out, you will significantly overestimate how much titrant needs to be added, and therefore you will overshoot and immediately start to form a buffer system. So instead, what we have on the right-hand side is a pH-dependent dampening function. So this goes between 0 and a maximum at zeta. Zeta is a dampening factor, which here has been set as 0.7. So that maxima is at the equivalence point between the two titrants, so sodium hydroxide and citric acid. The reason for this is if you can imagine you're on the steep section of the titration curve, then maybe this linear approximation is not a terrible idea. But if you are either ends, then it is going to be quite a significant overestimate, and so we want to dampen this. I'm also going to show a web application at the end of the talk, which has some hyperparameters like zeta. And the thing to bear in mind is we can actually control these to change how the algorithm performs. So for example, a higher value of zeta will mean less dampening, a more aggressive approach if we want to try and reach in fewer iterations, but the downside is we have a greater likelihood of overshooting. On the other side, on the other hand, we could decrease zeta, have more dampening, make the whole thing more conservative, and probably not overshoot, but take more iterations in total. So now we go to the Gaussian process regressor and the kind of true ML. So what we have here is something that I didn't mention on the previous slide, but the method is for all these three stages. On the right-hand side, we have the speciation diagram for citric acid. So at very high pH, citric acid is going to completely dissociate and release 3 protons. It's going to act as a very strong acid. At very low pH, say pH 1, pH 2, you can see it's completely in its deep, like H3A state. So it's not going to be very acidic, if at all. So we need to take this into account. So on the bottom here of the figure on the left, you see net moles of H plus slash OH minus. So if you have hydrochloric acid and NaOH, this computation is really straightforward to do. It's just number of moles equals concentration times volume. For citric acid, however, its number of moles is the volume of citric acid added times by the concentration, which we know, times by essentially an effective concentration, which will be given as a result of the speciation diagram, which has been solved, which has been computed through solving the material balances for the citric acid hydrolysis. So that's one way in which this method is physics informed. We are taking into account the physical chemistry of our system. Secondly, we know that a titration curve has this shape where it's kind of monotonically increasing, and we can exploit this information to have a linear and monotonically increasing mean function for the GP. And in this way, we make our ML methods more efficient through our domain knowledge. Now let's see what happens if we have a naive Bayesian optimization approach. So here I give you an example of an overshoot, and our method has to be able to also deal with overshoots, otherwise I would have wasted a lot of samples. So what we have here, let's see, okay, you can see my cursor. So this is 0.0. This is the initial pH. We add a little bit of acid, the pH didn't change much. We add, in this case actually it was 1 mil of acid, and pH changed a lot and it overshot, and we undershot the target. So what are we going to do? We're going to compensate and we're going to add base back. So we add some base. However, the problem here is we've already formed a complex buffer system and we added a milliliter of acid. And you can see from here, and I could see from when I was working in the lab, that we need to add more than a milliliter of base back. But a purely ML or purely statistical approach won't know this, because it's going to see that there's this point here, so it's expecting this very sharp jump, or push it any further right, this part, and there's going to be a discontinuity, so it's unphysical. So instead, we can just exit to an alternative strategy. So once we have an overshoot, which we can define as acid followed by base addition, so you know you have to go in the other direction or vice versa. So at this point, so initial, add acid, and then you added base. At this point instead, we will take beta here, which is calculated as the change in volume over the change in pH, times by the pH we're at, which is that point, to the pH we want to be at, times by another type of hyperparameter dampening factor here called mu. So with this, we're able to also deal with overshot samples. So now I'm going to summarize the results from this project. So what you can see from the figure on the left is the total number of iterations required to reach target pH. So given we're working with quite a complex chemistry, we are able to hit within pretty much 3 iterations the target pH if we don't have an overshoot. And even if we have an overshoot, it's only taking an additional 1 or 2 iterations for most of the samples. We have a few kind of extreme outliers, which are also interesting because those were formulations where already the ingredients contained some buffering agent, so they were very difficult to titrate. But on the whole, over hundreds of experiments, we can see a good performance, and we also see a broad distribution of initial pHs that we started at, and we were able to pretty much converge and get all the samples to the desired target pH. So this is something, especially maybe a year and a half ago, I couldn't have imagined, because typically these titrations, if anyone's been doing them in the lab, either in academia or even in industry, they're quite laborious, time-consuming. If you overshoot, often chemists will chuck them out and restart. So probably I would only want to do maybe tens of titrations manually. However, for this campaign where we have to produce hundreds of formulations, we needed such an automated, robotic, and machine learning-driven solution. So now we were interested in just taking this method and seeing, okay, it works on this 10 milliliter scale, but what about a more industry relevant scale of, say, 250 milliliters? So the 25 times scale up factor, and this is kind of close to the volumes used in industrial R&D labs. So we took the same method, and also actually even on your phones, if you scan the QR code on screen, it should open up a nice Streamlit web app. So what we did is I followed basically the recipe. So on the Streamlit app, you can, and I'll show you how that works. You can type in kind of what is the pH, how much acid or base did you add, what is the newly measured pH, and it will just suggest how much to add. It's pretty much the same strategy as on the pH bot. On the pH bot, it's executed automatically. Here, I'm executing it manually in a benchtop titration over here. And for all these 6 samples that I prepared at 250 ml, they were also all titrated to the target pH within about 2 to 4 iterations, which is great. In the middle panel, we logged the mixing time versus the apparent viscosity. So one would intuitively expect the more viscous the formulation, the greater the mixing time. What we can see loosely from this figure, and small set of points, is there is likely to be some sort of power law relationship as we've got a linear fit on the log-log axis. So this was wrapping up that part. So I will exit this. Okay, great. I just want to show you the web application. So I showed you and discussed for this, I've been using citric acid sodium hydroxide. However, the chemical equations can be written in maths, entirely general, and that's kind of the back end of this. So you can use different acids, including if we can use a weak acid, strong base, we should be able to use the simpler thing with strong acid, strong base, something like this. Realistically, one would never want to titrate with a weak acid, weak base, because this wouldn't make much sense. But you can have, say, monobasic acid, dibasic, citric acid is more complex tribasic. You have different choice of bases too, and we could easily add more acids and bases that you can work with. If anyone is actually interested in working with this, they can just ping me a message, and all I need to add is basically the Ka, Kb's, the acid-base dissociation constants, and the method is general. We can use, we can input the concentration of acid and base we're working with, what is the target pH. There's a couple of hyperparameters which can be modified if you wish with these sliders. In the preprint, we explain in further detail what is the implication of these things. And these are some instructions for how to use this. So I'm just going to give you a very quick demo. So say we start at pH 11. Also a live demo, so I hope this works. We start at pH 11. Going to add, it suggests a small random addition, say 2.4. Say the pH goes down to 10.5. In this version, one thing which is distinctly different is I have not constrained it, because this was also something I was using in the lab, and as a formulator, you have some domain experience that, okay, probably adding maybe 20 milliliters of acid for a 250 milliliter sample doesn't make sense, let me try 10 and remeasure. Whereas for the pH bot, these constraints were automatically encoded, so no human intervention was required. So let me try adding 10 milliliters of acid, say the pH goes down to 6.6. So this is where we would perform the experiment in the lab, add a further 2.3, and say we go to 5.7. And the adjustment is complete. So that's an example with the application. Let me get that on screen. So yeah, I'm about wrapped up. So here we have the confluence of lab automation, machine learning, and physical chemistry. So it allows us to do very exciting and cool things. It's been quite fun working at this intersection. And you have the pH bot as one example of how these things can come together to achieve the batch titration of viscous formulations with general acids and bases. So thank you all for your attention and for being here. And I welcome any questions that you may have. Thank you.